Mm-hmm. All right, we're live. Let's look at the mic. 1, 2, 3, 4, 5. Mic looks okay. Let's wait for YouTube to begin. Let's maybe refresh YouTube. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's kind of low. Why is it so low? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I don't see an issue here. It's not loud. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. No, mic is at 100%. So I don't know what's going on. I'm at 60%. Audio is at 60%. The laptop audio is 60%. YouTube doesn't say. It's about 60% too. So I don't know what's going on. Let's just begin. Okay, so I want to figure out the ultraviolet catastrophe. So I started looking into that. I saw that, who has a good video? Let me look into this. So this is going to be the ultraviolet catastrophe. Let's see who has a good video. Let's give her a chance.
Over 100 years ago, physicists were trying to figure out how things glow, like molten glass or hot lava. It seems like a simple question and was being pondered by such physicists as Lord Rayleigh at the turn of the 20th century.
I give you a wooden skewer that, when touched to a flame, glows orange-red.
Rayleigh knew that the color of this glow depends on temperature. Like the sun that has a surface temperature of 5,500 degrees Celsius radiates a bunch of different colors that together...
I don't understand why these people need to always have visual effects. Why is she holding a piece of glass talking about the sun? This is so confusing. Why can't you just show an experiment and explain the experiment? I mean, how difficult is that? Why are these people so bizarre? Really weird. And I don't know what she's trying to say.
Look white to us. Or me, at 37 degrees Celsius, I have this invisible halo of infrared light. Fun fact...
Okay, so she has a halo, okay.
Infrared light is invisible to humans, but snakes can actually sense it from up to...
Okay, why is she talking about snakes? This should be a very straightforward discussion. Why are they switching topics?
...a meter away to detect prey. Rayleigh wanted to understand where the light came from and come up with a rule that would predict how much of each color it would...
What is she showing? What is this? This is... there's no X, there's no Y, no indication. What is this?
...emit.
How did they plot this curve? Okay, this is a waste of time.
Colors that...
This is the good one.
Frequencies
Physics
of the EM
explained.
radiation
Okay.
and therefore
Let's start from the
frequencies
beginning.
of the EM radiation inside the cube. James Clerk Maxwell's grand... Towards the end of the 19th century, physics was flourishing. The principles of thermodynamics had helped to kickstart the Industrial Revolution, and Faraday had
Let's just make sure the audio is okay.
The principles of thermodynamics had helped to
Okay, sounds good.
recently discovered how to generate electricity. Furthermore, James Clerk Maxwell's grand unification of electricity and magnetism had led to the remarkable realization that light was an electromagnetic wave. Spurred on by the power and reach of these new theories, physicists began using them to address some of the big unsolved problems of the day. One such problem involved explaining how hot objects emit light. It was well known that if you heat a lump of metal, it will first glow dull red, Then orange
Okay, so they figured out that light is electromagnetic wave. Okay. Now they want to figure out how and why things glow. Okay, so the electromagnetic wave theory would suggest that electrons or atoms are being vibrated. The electrons are the ones that vibrate, and the electrons are, this vibration heats them up or causes them to go up in one orbit and then they drop in orbit. But maybe I know too much. Maybe they had no idea how it works. I mean, ultimately, I think that's Bohr's atomic model. But they had no idea. So it's difficult to understand what they didn't understand. So they had no idea why it glows. Where is the electromagnetic wave coming from? Well, an electron is vibrating and is causing an electromagnetic wave. I don't even need to say that it's going from one orbit to another. All I need to say is that I'm heating something up, the atoms are vibrating, therefore the electrons are vibrating, therefore the electrons are emitting, right? The electrons are creating waves in the electromagnetic field.
orangey red, then yellow, and eventually bluey white at the same time as getting brighter. Physicists wanted to explain how the intensity or brightness of the emitted radiation related to the wavelength or color. They realized
It's not good to say wavelength, they should say color. So the question is, how does the intensity change the wavelength? Well, it looks like the intensity changes the color directly. The more the intensity, the more the frequency, right? This is a high frequency compared to this. This is basically red, which is low frequency, and this is white or blue when it's high frequency, right? And here it is. There is the plot. So this is the temperature, and this is the wavelength, even though they don't say it's the wavelength. So as the temperature rises, the wavelength increases. So it's basically a straight line upwards.
that this would involve understanding how matter, the lump of metal, interacts with radiation, the light emitted, at a fundamental level. However, when Maxwell's theory was used in conjunction with classical thermodynamics to calculate the emission profile of a hot object, it predicted that all such objects should be emitting an infinite amount of energy at small wavelengths or high
This doesn't make any sense. This is high wavelength. It should be linear. The greater the intensity, meaning the greater the heat, the temperature, the greater the wavelength. Why would you predict? This is the prediction?
objects should be emitting an infinite amount of energy at small wavelengths or high frequencies.
Oh wait, the wavelength is greater, so no, it's opposite. Yeah, this is the prediction. This is not the color. This is 1 over the color. So this is the wavelength. Good, yeah. So this is correct. So the higher the intensity, the lower the wavelength, meaning the higher the frequency, the whiter the color, the bluer the color. So this is red and this is blue. Yeah, this makes perfect sense.
Because high frequency light was dubbed ultraviolet light, and because
Okay, high frequency is over here. So this is the ultraviolet. So the ultraviolet, yeah.
this prediction was clearly problematic, this issue became known as the ultraviolet catastrophe.
Why is it problematic? I mean, where's the issue? The greater the intensity, you should get smaller and smaller wavelengths. Asymptotically, what's the issue? Why is it an ultraviolet catastrophe? What's the issue?
It represented a complete failure of classical physics, and it was in attempting to solve this problem that Max Planck was forced to introduce
I don't
ultraviolet
understand.
frequencies
Understand.
should be emitting an infinite amount of energy at small wavelengths.
What do you mean infinite amount of energy? I don't understand. I don't understand. The wavelength should be smaller and smaller. I mean, what do you mean should be? You see that this is the fact. You see it here. This is the experiment. You see that the greater the intensity, the shorter the wavelength. Why here? The greater the intensity, the shorter the wavelength. The greater the intensity, the shorter the wavelength. So yeah, it's something like this. What's the problem?
Or high frequency together acts with radiation, the light is stand and eventually bluey white at the same time as getting brighter. Physicists wanted to explain how the intensity or brightness of the emitted radiation related to the wavelength or colour. They realised that this would involve understanding how matter, the lump of metal, interacts with radiation, the light emitted, at a fundamental.
So the more you jiggle an electron or an atom, the more it vibrates, the faster it vibrates, the wider the color, the smaller the wavelength.
Mental level. However, when Maxwell's theory was used in conjunction with classical thermodynamics,
So, I mean, all that you need from Maxwell is that blue shift and white shift is just high frequency. Light is an electromagnetic wave. So in order to create an electromagnetic wave, you just need to shake an electron, which is shaking, right? I don't know what they knew about the atomic model, but thermodynamics, they knew that it's shaking, that heat is the shaking. I'm assuming they know heat is the shaking of the atoms. So where's the issue?
to calculate the emission profile of a hot object, it predicted that all such objects should be emitting an infinite amount of energy at.
This doesn't make any sense. Energy is the input. 1 second, somebody's talking to us. So wait. Oh, I need to talk to Blush. 1 second. Let's see, how is Hamburger? And now I need to talk privately to Blush. One second. Okay, let me see what she responds. Loca loca, chica loca, loca loca, chica loca. Okay. You know what? I'll use my phone to communicate with her so I don't interrupt the broadcast. Loca loca, chica loca. Loca loca, chica loca. I don't see a response. Okay. So let's see. Okay, we were here. Oh, wow, that's her lunch. Wow. La, 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 la. Wow, good food, very good. Delicious, looks delicious. Alright, so, what do you mean by, I don't understand his last statement, this is so confusing.
Physical thermodynamics to calculate the emission profile of a hot object, it predicted that all such objects should be emitting an infinite amount of energy at small wavelengths.
What do you mean an infinite amount of energy? I don't know what it means, an infinite amount of energy. I don't know what they're talking about. I don't know what they're talking about. Here is reality. Reality is there's no infinities in reality. The heat, the intensity, the heat per unit volume or something. It's whatever it is, and at this level, it's whatever wavelength, it's whatever color. So I don't know what they're talking about. What do you mean infinity? I mean, if you increase in intensity to infinity, you're gonna get shorter and shorter. As intensity goes to infinity, the wavelength goes to zero. Yeah, makes perfect sense. So at one point, this is going to emit gamma rays. I think that's the shortest wavelength you can get. I don't know if that's true, but if you can through just heat cause this to vibrate, but because usually I don't know if we have the ability to heat like steel so much that it emits. I don't know, even ultraviolet, I don't know if it emits. 1 second, let me see. It's going well, that's good. Let me respond to Hamburger. Let me see what Hamburger is saying. Hamburger. I'm streaming. You want to join and tell us about your life. Boca boca, chica boca, loca loca, chica loca. Oh, alright, soon we're gonna have Senis with us. Senis is eating something and then is joining us. I don't understand the issue.
Or high frequencies. Because high frequency light was dubbed ultraviolet light, and because this prediction was clearly problematic.
Where is the problem? God help me, where is the problem?
This issue became known as the ultraviolet.
What is the catastrophe? This is very terribly explained. I don't see a catastrophe. I don't see any issue.
Catastrophe. It represented a complete failure of classical physics, and it was in attempting to solve.
Why is it a complete failure of classical physics?
This problem that Max Planck was forced to introduce the revolutionary concept of energy quantization.
Oh, I think this is just an overview, and now he's going to go into details.
The idea that energy is transferred discretely in chunks rather than continuously. After Planck's work on this topic, the world would never be the same again. In order to properly understand Planck's solution to the problem and why this represents such an important turning point in the history of science, we first need to understand the cause of the problem. And to understand the cause, we need to start with some basics. When you shine light on an object, some of it may be reflected, some of it may be transmitted, and some of it may be absorbed. Darker objects tend to absorb more of the light incident upon them and reflect less than lighter objects, which is why they appear dark in the first place, but also why they tend to heat up more quickly. Think about how black surfaces heat up in the summer compared with white surfaces. An object that absorbs all of the light incident upon it is referred to by physicists as a black body, for obvious reasons. If the temperature of a black body is less than the temperature of the environment in which it is placed, then it will continue to absorb energy from the environment until it has reached the same temperature, at which stage it is said to be in thermal equilibrium.
Mm-hmm.
If, however, the black body has a temperature which is higher than its surroundings,
Mm-hmm.
then it will radiate energy away until it has lowered it.
1 second, let me check messages. Okay, Hamburger says, hell yeah. Alright, Hamburger is with us. 1 second, let me go to here and share this tab. Hey, Hamburger, what's up?
Hey, Slave.
Hey, how is your life?
Okay. I think I had somewhat of a depressive episode, but I think I'm fine.
Wait, right now you're experiencing depression?
No, more like a few days ago.
So a few days ago you had depression?
It's not like depression, it's like an episode of like very intense depression. Like it's not like gradual.
Mm-hmm.
It's just like sudden onset and usually triggered by something that's like because I have PTSD, so it's sort of just like something
Mm-hmm.
reminds you of a trauma and you kind of spiral for a little bit. So I had like a few days on my own, and I think that helped.
That's good.
Yeah.
So you have PTSD?
Uh-huh.
From what?
Badly.
From what?
I had like a lot of problems growing up, so it's mostly from like child neglect and abuse. And then also like more recently, like when my dad died, I was home alone and he had a brain aneurysm on the staircase, so I was the only person at home and his head was like split open in the basement.
Oh, I'm sorry. Wait, could you
So that
wait?
traumatized me a lot,
I
like
see.
differently.
Wait, could you just hold on because I have I have somebody else chatting with me in the private DMs.
Ooh.
Let me ask her if she wants to join.
Yeah, you
Uh,
never have anyone else.
right, this one
That's
maybe
usually my hours, honestly. Like
what?
you're popular, just not like when I'm around.
No, I haven't been here in a couple of days. Let me just Amber. I'm gonna tell her I'm talking with Amber.
Is it someone I know?
I don't know. I don't know if she wants anyone to know. Like
Uh,
we have like I don't want to say anything because anything I'll say could jeopardize everything. So um
I
um
gotcha.
yeah. Okay. Let me just ask her. Can I call you later? Okay. She's probably gonna get very upset. But she might be watching the YouTube channel right now. So I need to.
If she is watching, I hope she's not upset.
Yeah, I hope so too. Anyway, um, so you. Oh my God! So you had a really traumatic childhood.
Yeah.
Mm. So because of that, you suffer like depression episodes.
Yeah.
Yeah, yeah. But you're not moody. You're always very nice.
Um, uh, I guess that's true, but that's because you deserve it. You don't like disrespect me. Other people are disrespectful to me, and
Mm.
then they think that my anger is like moodiness or a mood swing, as if they should be allowed to just openly insult me and it not change my mood.
Mm.
Like I always tell people, like I'm not a fucking sociopath. I can't just like not be upset that you insulted me or something.
Mhm. Mhm.
But it's nice to hear you say that.
Nice to hear me say that you're never moody, that you're always very nice. Well, statistically
Oh yeah,
speaking,
I get like a lot of people, not a lot of people honestly, but like people are just louder about it when they want to be.
hmm
And mostly it's just like Discord trolls and like stupid crap, but it's also like a criticism my parents would have given me. Where they would qualify like something as like a mood swing, but like maybe they insulted me like all day long or like, made me do something inappropriate.
wait, your parents made you do inappropriate things?
Yeah, like I didn't realize it wasn't normal to like have to take care of your entire family, and like also my mom was an alcoholic
Hmm.
and she would have me with her boyfriends and shit like all day when she would leave to go to her job. And then like they would just like do like things to me like I'm gonna just straight up say it was like abusive,
hmm
but like I don't like when people like debate me on like the term, because some people are like that's not really being violated if it wasn't like penetration, but I'm just like, yeah, it wasn't appropriate. And
hmm
it's also not to say that there wasn't penetration, it's just the fact I can't remember it because I have like that, you know
hmm
like I don't have the ability to remember it essentially. Like I'll remember like random stuff on a Tuesday sometimes, and that just really sucks. Like I had nightmares about one of her boyfriends a few nights ago, like before my fiance went on a business trip.
hmm
And it was just really weird. It was like I couldn't see myself. I couldn't see anyone else. But I could see like the backs of two people and they were trying to get me to remember what his name was. And then I woke up remembering his name. And I was like, why is my brain trying to get me to remember this when there's nothing I can do about it basically.
Mm.
But you know,
hmm
uh, it's really hard because it's like part of me wants to remember things so I can be upset.
hmm
Because my parents tell me there's nothing to be upset over and that nothing ever happened to me. But if I bring it up, they like freak out and give me this like, what do you want me to do about it reaction? And it's like, I want you to just treat me like a person. Like, like if I had a child and they told me they were violated by an adult, like I wouldn't scream at them and make it like their fault.
Wait,
Because like there's just like nothing I can do about it because they're like their first thing is like you didn't tell us, and it's like yes I did tell you.
wait, one
I
second.
was just a child,
Wait,
so
I have so many questions. Wait, but do people call you Bergie?
no, it's call me Burger.
No, but because she's asking if your name is Bergie.
No,
Then she doesn't
that
know
might be a
you.
different person or something.
Oh, okay. I'll
Can you
tell.
tell her I was a girl? It made it like more obvious.
Well, I think she knows. Well, hamburger. Well, it's
Some
uh.
people don't catch on to that. They just think it's hamburger without an H.
Mm, she says, "Okay, talk to you later." So just, I think I survived, so I'm gonna be fine. So
No.
wait a minute. So you're asking why does your brain want you suddenly to remember his name or whose name? His name?
Yeah, it's just like one of my mom's like ex-boyfriends.
One second. Hey, Sanas, what's up?
Hey, are you
Hey,
listening?
am I listening or you're listening?
Yeah, can you hear me?
Oh, can I hear you? Not as well
Yeah.
as Hamburger,
Oh, okay. That's
but
usual, probably.
no, I mean we'll survive. Hey, Hamburger, Sanas, how much time do you have now to work?
Until the end of the day.
Okay, that's good.
We can continue our conversation.
No, 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 no. We really need to finish this paper. Hamburger, your comment about why your brain wants you to remember this, this is actually my line of research. So I'd love to talk to you about it.
Yeah, I guess let's stick a pin in it, and then
Yeah,
maybe after your physics discussion, that would be like a welcome break.
yeah. Because we need to finish this paper because this is absolutely revolutionary, and I need to do this revolution to save the universe.
You gotta make sure you make your like physics lives all in one playlist so I can catch up on it one day.
No, no, it's impossible. It's so much. It's mostly just writing the paper. It's mostly very, very like it's literature. It's technical writing.
Yeah,
One second.
I tried to look and it was like hours of shit.
Yeah. One second. Let me just tell people are asking me IRL what's happening with me, so I need to tell them I'm busy. One second. Okay. Anyway, so let's do this. So let me work with Senes, and next time I'm live, I'll call you and we'll continue. Hamburger.
Yeah, cool, dude. Talk to you
Alright.
later.
Alright, talk to you later. Thank you. Take care. Bye. Alright, Senes.
Alright. You want me to join the StreamYard? Or
One
will do
second.
it?
Let me just ask. Uh, um, Let me just see what she says. Okay, they're gonna write a text and I'll know the problem. It's amazing. I go live. No one is talking to me. And then one person hops in, and now everybody wants to talk to me live, IRL. It's like, which is, I mean, it's good. It's better than having
Prime
no one
time.
to talk to. Anyway, okay, so I started watching uh, this thing. I don't know if you're watching the ultraviolet catastrophe, or do you want to continue writing the paper? My preference is to get back to writing the paper. That's the most. As
I've
long
read the paper, yes.
Yeah, let's do the paper. One second. Uh, uh, okay, let's continue. So let me pull up the paper. So you need to join the stream. So let me
Yeah,
give
okay.
you the link. I'll give the link publicly,
You put
and
where will you put the link?
I'll put the link here in the room too. I think
Okay.
it's the right one. Yeah. So you click. You click the one that ends with ME. The link that ends with
Yeah,
ME. That's
I
the one.
already clicked.
Okay.
Wait.
Let me clear this. And let me see when you pop in. I'll see you.
Okay, I will leave you.
Okay. Alright, so let me turn on. Okay, there you are.
Alright. Yeah.
Alright.
Yeah.
So here is work offline, turn on offline, reload, share this tab. Let me. Oh my god. Yeah, let me just see what's going on because I'm trying to create a very important deal in real life. Let me see. Let me see. Let me see. Mm. One second. What? All right. One second. She wants a phone number. 1 second. It's this one. Okay. Let me just ask her. Okay, let's go. Enough nonsense. Okay, so can you see? Yeah, you can see it. Okay.
Yeah.
So proof of Einstein's special relativity's second postulate. Oh, by the way, so today I was watching, like it popped into my my YouTube feed, a video from a year ago by Lenny Susskind. Where's the history? Here, let me show you. There's a handstand, very important handstand. Was I watching it on my other phone? I don't believe it. Could not have been on my other phone. I guess it was? I usually don't watch physics on my other phone.
Oh, Leonard
Anyway,
says-
no, this is an amazing interview. That's irrelevant. That's from last night. Lenny Susskind. I mean,
no, the video above it.
this one, Roger Penrose. I
No,
hate
no,
Roger.
yeah.
No, Lenny Susskind. You need to listen to this. This is such an incredible life story. This is unbelievable.
I don't know. I
Anyway,
don't know who he is.
You don't know Lenny
Well,
Lenny
there's
Susskind?
another one of Lenny Susskind above. Maybe
What?
it's that one. There's
Wait,
another
speak
one
louder.
above. There's another one above of him.
No. This
No,
is
above,
Roger.
like you need to go up.
Yo, what's up, bro?
Hey, 1 second. What's up, Nick?
How you doing?
I'm okay. But you wanna? Well, I mean, I'd love to invite you to the stream, but you're gonna start talking about Planck's constant and Planck, and we're busy writing the paper. Anyway, I gotta get back to the stream. I wanted to talk to you, but like everybody's talking to me at once, so I can't. How's your life, Nick?
Pretty good, pretty good.
That's good. That's good. Anyway, I'll next time I'm online and there's no one here, I'll call you and we can talk about anything you want. But
That sounds good.
yeah, for now, let me get back to CNES. I'll talk to you later, man.
Yep. Bye bye.
Alright, bye. This anyway. So let me just look up the specific video.
Yeah, there was. I was telling you, there was one video. Okay, so now you moved above, but in the middle of between now where you are and where you were, there is another video of Susskind.
Where?
A little bit down, a little bit down.
This one? Cops
no,
owned?
No, below.
Oh, you're right. Yeah. This one, yes. Good job. So, 1 second. 1 second.
So who's this guy? Is he a physicist?
Lenny Susskind?
Yeah.
He's one of my maybe favorite physicists. Anyway, look at this lecture. Leonard Susskind, astonishing lecture on debunking quantum gravity. They're not gonna let me work.
Okay, interesting.
So you know who else had lectures about debunking quantum gravity?
Well, Einstein. No, that was well after Einstein, probably. Well,
So let me open a
can I?
new one. You can keep guessing. Let me just write debunking quantum gravity. Let me see who else had lectures about it. What is quantum gravity? Let's see if anybody else debunks. Let me see how quantum complexity found its way into black hole physics 5 months ago. Quantum gravity, new gravity.
Oh, maybe that guy, what's his? He has a weird name.
Uni? I don't know anyone uni.
Yeah, it was above.
I don't see
Like
anyone
a physicist
debunking.
that is a little bit out of the mainstream.
I don't see anyone who debunks quantum gravity.
No, you're not gonna see it in the first like 100 YouTube videos. Wow.
Anyway, so I'll tell you who does debunk quantum gravity. So let me see. Oops. Let me switch to.
Oh, you debunk quantum gravity. Okay, that was the case.
Let me see. Debunk. More debunking of black hole singularity. Debunking. Debate about black hole formation. Debunking the black hole singularity and quantum gravity. This is from a year ago. Look, I didn't completely debunk quantum gravity, but my intuition always was that quantum gravity.
Yeah, what's the idea of quantum gravity? Is the gravitons thing?
Yeah, yeah.
I mean, that's silly.
Yeah.
Like, that's just what quantum physicists do. They make up a new particle. When in doubt, make a new particle.
No, it's okay to have a
Yeah,
what's it called?
It gets
No, it's
it
okay.
gets pretty obvious what they're doing at some point.
No, it's okay. One second. It's okay to have a graviton. A graviton is. I don't deny that you can create a graviton. Let me just check if I have anything interesting. I don't deny that you could get a He doesn't. I don't think he denies a graviton. Let's go back to what he says. Anyway, but I wouldn't say that I was able. Let me see. Also, I discussed ghosts. Blah, blah, blah. I don't remember if I successfully debunked quantum gravity. But I don't know what people mean by quantum gravity. If they people think that. I don't know. It doesn't matter. We already explained that Einstein's GR actually works at the quantum scale. There's no issue showing GR working at the quantum scale. There's no issue. I mean, GR for me says that the ether annihilates upon contacting a massive object. And a massive object is just an object that interacts with the Higgs mechanism. So the Higgs mechanism destroys, annihilates the ether. So the way that ether gives objects mass is through annihilating itself. So the ether annihilates itself. That is the Higgs mechanism. And this annihilation is gravity. So that is quantum gravity. So gravity is always quantum. And this is GR. There's no contradiction. Do you want me to
There
draw?
is no contradiction, but
Do you want me to draw this?
so inertia is caused by ether annihilation in your theory. So how would that work?
Yes.
How would that work mechanically?
That's a good question. How does what is inertia? Is okay. So inertia
Is resistance
what
to movement.
I think that
speed.
What?
Is resistance to change in speed.
Yes. So Inertia.
I mean, if the ether is constantly moving towards objects and it has some effect on them, but it becomes at rest with them quite rather quickly, then it would only
Wait,
be
what?
changes
Wait. Start over.
okay, if the ether moves towards objects but then
Yeah.
becomes at rest with them
Wait,
rather
what?
quickly.
No. I don't. Speak slower.
Okay, if the ether moves towards objects,
Okay.
but then at some point either annihilates itself on the objects
Yes.
or becomes at rest with them,
No.
that's still a possibility. You say no to that,
No.
but
Otherwise, no.
it
It
still
has
works.
to. It has to annihilate. It has to annihilate because otherwise you cannot get gravity.
Yes, it
How?
works both ways in this case.
Okay.
Just setting up conditions in which it works. In this case, it works with both theories.
What do you mean both
Uh,
theories? What do you mean both theories?
the theory that it would be at rest and the theory that it would annihilate itself. It would
No.
work with both theories.
No. 1 second. Let me just see. I have a message. Okay.
But okay, forget about that. Let's just say the annihilation theory. If the ether
Yes.
moves towards objects and gets annihilated,
But that's not
then
how it. No, that's not it. Because the ether cannot move towards an object. The ether has to interact with an object and annihilate. Through the annihilation, a vacuum ether is created.
yes.
This vacuum is in effect low pressure ether. And
So
dark energy, 1 second. And dark energy is high pressure ether. So you have a pressure gradient. And this is when the ether starts flowing into the object that it just annihilated by interacting with it. And this is now gravity. Now, the very interaction is giving it inertia. The very interaction gives it inertia, and this very interaction annihilates. So through the interaction, it gives it inertia and annihilates, and therefore gives it gravity, gives it inertial
So
and
this would still mean that, especially at lower speeds, when there is no relativistic effect, the ether would move. The speed of the ether moving towards an object would be in accordance to the speed of the object.
no, no, no,
Yes,
no.
it has to work like that.
Wait, repeat the statement. What did you say?
Okay, at low velocities,
What do you mean? What do you mean at low
especially at low velocities, I'm trying not to consider the relativistic mass effect
No,
for
no,
now.
no. There is no. This is relative to the ether. So let's say we're talking stationary at rest relative to the ether.
Okay,
So
but it's something, but we have to understand the nature of inertia. So if
Okay.
something is
let's
moving,
talk about. Wait. Let's talk about the electron, and let's say it's not moving. Right? It doesn't matter if it's moving or not.
Okay.
Inertia is wanting to the object's will to stay in whatever, either moving or at rest. That's inertia. There is no difference between moving and being at rest.
okay, but we have to explain why there is no difference. Like, what's the mechanism?
Fine, we can get there, but let's talk about the electron at rest relative to the ether.
Okay.
And the electron has very little interaction with the Higgs mechanism of the ether. Now, the Higgs mechanism, all it does, the way it works, the way it gives objects their mass, let's draw this. So basically, let's say you have an electron. Initially, the electron has no mass. It's massless. All elementary particles, before the Higgs mechanism is introduced into the discussion, they have zero mass. Their mass
You
is
have to
how...
explain the Higgs mechanism to me.
Wait,
Because
what?
I never searched the Higgs mechanism. So
I'm
yeah.
explaining to you the Higgs mechanism. This is my understanding of the Higgs mechanism. And by the way, the best video is PBS Spacetime. They had and we can then, if you want, we can go watch. But let
No,
me
you
try
can
to
explain it. Yeah,
I'll explain and
it's
then we can watch, because Higgs is really important. So the Higgs mechanism is a mechanism of the ether. So all it does, it just causes this electron, massless electron, to just bounce, to just jiggle around in every which three-dimensional direction. It
Like
just
expanding or
no. It just bounces
just
it
oh,
back
okay.
and forth.
Vibrates.
It's just causing it to vibrate around this location. It's just causing it to vibrate. That's all. This is basically mass. Why is that? Because so initially an electron, because it's massless, it actually wants to move at the speed of light. All massless particles, well, it's not really a particle. So initially it's really a wave, some sort of a wave. Let's say it's a three-dimensional spherical wave. It wants to expand at the speed of light as just as a Maxwell's electromagnetic wave. That's what it initially wants to do. However, because of the Higgs mechanism, the Higgs interacts with it, and I think it causes the wave to collapse. So you get the particle shows up. Right? So you can have a wave, and if you interact with it, you can cause a particle to show up. If you interact with a wave, then the particle shows up. The wave collapses, or in the words of Schrödinger, the wave function collapses, and a particle shows up.
Okay, a particle shows up, but
and this is the electron, right? Because
what about that?
What?
But what about that? So the particle shows up, then what?
And then it starts waving again. It starts waving again, and again it interacts with the Higgs mechanism, and the particle shows up again. And again it starts waving, and again it interacts, and the Higgs basically doesn't let it move. And the Higgs makes it pop up and disappear, pop up and disappear, and between every time it shows up, it's a wave. So but it's bouncing around. Now, the more it interacts with the Higgs, the more local it becomes, and the more mass we say it has. The less it interacts, the more it jumps around, and the weightless we say it is. The less inertia. Right? You can imagine that the more, like a particle that is very, very heavy, so it basically never moves. So initially it wants to move at the speed of light, it wants to fly away, but if it's very heavy, meaning if it interacts with the Higgs intensely, then it's going to end up not going anywhere. It's not going to move at the speed of light. It's actually going to be stationary relative to the ether. Now, this has nothing to do whether it's moving or not moving. It's the same interaction, certainly relative to us, because of our clocks. So if we're moving together, if I'm moving at the same speed as the electron, then because my clocks are slowing down, then it's going to look like it's stationary. Everything that has to do with this electron is going to appear stationary. Even though as the electron is moving, its clock, its interaction, its internals slow down. So let's ignore. I'm not gonna try and figure out relativity. This, and by the way, this
looks like completely made up.
No.
No, not from you, but
no.
This looks like it's a nice hypothesis, but like whatever, we don't know if it works.
No. This is QFT, so I don't know QFT enough. I know very little QFT. 1 second, let me look at the message. One second, let me just. Okay. So by the way, I don't know. I know very little QFT, quantum field theory, but this is quantum field theory. I mean, the Higgs mechanism is.
That's not what I'm saying. I think that's going to feel theory. What I'm saying is that this looks like just, yeah, it's a nice hypothesis, but does it work like that?
So give me a second. Let me just. All right. Let's get back to work. All right. So this is quantum field theory. This is the Higgs mechanism. This is just the way I understand it, but I'm not contradicting. All I'm saying is this is, instead of saying it's the Higgs mechanism, I'm saying it's the Higgs mechanism of the ether. That's all I'm saying. I'm just saying it's the Higgs mechanism of the ether, because for me everything is the ether. The quantum field is the ether, is gravity, just as Einstein said basically in 1920 in Leiden in his lecture at Lorenz's University. Except for he said the ether is not flowing, and I'm saying the ether is flowing. Okay. So that's the way I interpret the Higgs mechanism. Now let's watch. You know what? Let me find. Let me find. What's their name? PBS.
PBS space-time.
PBS space-time. PBS space-time Higgs. The Higgs mechanism. So by the way, they, based on their theory, they predicted a 125 giga-electron volt Higgs boson, and they found it. So, you know, that is the gold standard. They built the LHC.
I think you can find anything on.
No, but they said it's going to be 125 GeVs. So, look, I don't know. I honestly don't know enough. What?
I think you can find anything on a proton collision.
No, but I don't know. Anyway, it's a good explanation. I like the mechanism. The mechanism sounds good. This is a good mechanism to create gravity.
Yeah, it's just not bad. It's just like
I never heard of another explanation. So, you know, as far as I'm concerned, it's the only explanation. Let's try to listen to this. This is from 8 years ago.
Yeah, it was a long
No, I
time
think
ago.
it's this one. This is from 2 years ago. Let's
Okay,
listen to
maybe
this
new
one. Yeah.
Fermilab physicists really care about the mass of the W boson. They spent nearly a decade recording collisions at the Tevatron Collider and another decade analyzing the data. This culminated in the April 7th announcement that this obscure particle's mass seems to be 0.1% heavier than expected. So why do we care? Well, because understanding why this particle even has mass was one of the most important breakthroughs in our understanding of the subatomic world, and because measuring its precise mass either doubles down on our current understanding or reveals a path to even deeper knowledge. The Fermilab discrepancy is a tantalizing hint of the latter.
I don't know if this has to do with the you know, exactly how, but the title says how the Higgs mechanism gives things mass.
The timing of Fermilab's discovery is weirdly convenient. Over several previous episodes, we've been building towards an understanding of how the forces of nature are unified. The most powerful clue driving this is the weirdness of the weak force, in particular, the particles that carry this force. Its W and Z bosons have a property that we once thought no force-carrying particle should have. They have mass. The The W bosons are especially weak and they also have electric charge. This allows the weak force to trespass on the province of electromagnetism, suggesting a connection between the two. This connection hints at a unification of the forces of nature. The path to that unification leads to the Higgs mechanism, which not only explains the mass of the weak bosons, but teaches us about the nature of mass itself. To get to all that good stuff, we need a bit of a refresher on the episodes that led to this. Fields and forces and symmetries and all that. Similar to how the fabric of a drum has vibrational modes, so does the fabric of reality. Every point in space can wiggle, twist, and oscillate in different ways. A quantum field just represents one of these modes. These wiggles are quantized. They come in discrete packets of energy that can move around, and those are the particles of the field. One special type of field is the gauge field. These arise from the fact that physics often doesn't care what coordinate system you use. The laws of physics are symmetric under certain transformations. For example, physics works the same no matter where you decide to center your XYZ axes, or where you put the 0 point of your angles in polar coordinates. We saw in our episode on Noether's theorem that these symmetries lead to conservation laws. In quantum mechanics, this sort of redundant degree of freedom leads to a gauge field. We've seen an example of this. The exact phase of the quantum wave function from one point
No, I don't think this is the video I'm looking for.
space to the next local phase
It's a good video, but we need to watch it at one time or another.
doesn't affect measurable quantities, only relative phase matters. When we enforce this requirement, we find that we have to add a new quantum field to the Schrödinger equation that lets the universe counteract these phase shifts. That gauge field turns out to be electromagnetism, and oscillations in this field are the photon, our first gauge boson and carrier of the electromagnetic force. So, one of the fundamental forces arises from a symmetry of nature, in this case the fact that the laws of physics are invariant under changes of local phase. The set of
I have no idea what he's talking about. Forget it. Let's go watch.
Well, he's giving an introduction.
Yeah, but I don't think it's the video that I watched that I liked. Maybe this one.
We saw in a previous episode that most of the mass in your body, in fact the mass of anything that's made of atoms, doesn't come from the mass of the elementary particles. The electrons and the quarks that comprise protons and neutrons do seem to have intrinsic mass, but this is only around 1% of the mass of the atom. Most of the atom's mass is the confined kinetic and binding energy of those quarks. Now, today, I want to talk about this so-called intrinsic mass of the elementary particles. I want to show you that even in this case, mass is still just bound or confined energy. In the case of the constituents of the atom, it comes from the Higgs field. So, let's get to the bottom of this whole Higgs business. To understand how all this works, we're going to need to learn a bit of quantum field theory. Just the basics for now, we'll get into it in more detail another time. Now, QFT describes the fundamental particles as excitations in fields that fill our entire universe. For example, the electron is an excitation in the electron field. Imagine that every point in the universe has a certain level of electronness. In empty space, that level hovers around zero, but even in a vacuum, the electron field...
It's just a wave. I don't know why he needs to. It's just a wave. It's just a spherical wave.
That's the part, like, at this point might as well try to unify all those fields into something.
Yeah, I don't know. I mean, it's just a wave. I don't know why they show it like it's vibrating like that. But I don't know if he's talking about before it's given mass or after. Anyway.
Field is there. But now, add some energy to that field at a particular spot, as like plucking a guitar string. The field vibrates, and that vibration is our electron. And it's not just electrons. Every elementary particle is a vibration in its own field. And these vibrations and fields...
I don't know why he says in its own field. You cannot have multiple fields overlapping. You can only have one field in the universe, and that is, as far as I'm concerned, that's the ether. So I don't know why he has...
You could technically have fields overlapping.
How?
I mean, you can have a magnetic field and a gravitational field overlapping.
No, these are just... Right, I don't see how it's possible. I cannot imagine it.
Fields interact with each other, transferring energy, momentum, charge, etc. between particles and fields.
Why do you need them to interact with each other? Just have them be the same field.
Now, this is a very simplistic explanation of a theory that has produced an astoundingly accurate description of the subatomic universe. Given its incredible success, it was strange that quantum field theory, as it stood in the 1950s, gave a perfect description of the electron, and yet predicted that the electron should have no mass. The basic QFT equations of all the components of the atom leave them massless. As we'll see in the next couple of episodes, this masslessness means that particles should travel only at the speed of light and experience no time. Their clocks should be frozen. But these particles are distinctly not timeless. They evolve. Take the electron. It has this type of intrinsic quantum spin that we call chirality, and this can either be clockwise or counterclockwise relative to the direction of motion. We call this left-handedness or right-handedness. Now, that spin...
Relative to the direction of motion?
Yeah, the direction of motion is kind of strange.
That's not possible. You know, in the Stern-Gerlach experiment, the direction is anywhere, and the direction of motion is through the magnets.
No, but it works in that experiment, yes.
I never heard of this. Okay.
It constantly flips back and forth. The electron evolves, meaning it does experience time, so it must have mass. Also, we've weighed it. We've measured that mass directly. But a different sort of changeability is the only way that we know that it's time. It has this type of experience no time. Their clocks should be frozen. But these particles are distinctly not timeless. They evolve. Take the electron. It has this type of intrinsic quantum spin that we call chirality. And this can either be clockwise or counterclockwise relative to the direction of motion. We call this left-handedness or right-handedness. Now, that spin constantly flips back and forth. The electron evolves, meaning it does experience time, so it must have mass.
How does it switch back and forth?
Also, we've weighed it. We've measured that mass directly. But a different sort of changeability is the...
I mean, it has to change its angular momentum, but angular momentum must be conserved. So it must be interacting with something to switch this chirality.
Only way that we know that the tiny neutrino has mass, and it was the measurement of...
those neutrino oscillations that won the 2015 Nobel Prize in Physics. Now take the photon. It is definitely massless. It travels at the speed of light and it experiences its entire existence in an instant. It undergoes no internal evolution. It has spin, but the spin never flips. A photon only changes if it bumps into something else. But the photon and the electron are both just excitations in their own fields. So why does the electron have mass and the photon not? Why did the electron evolve? There are different ways to interpret it. But perhaps the simplest is to say that while the photon can cross the entire observable universe without bumping into a single thing, the electron is never not bumping into things. There's something in the substrate of space everywhere that impedes the electron. It's the Higgs field. To understand how this works, we need to...
You don't need to say that. I mean, space is obviously there's something there. Otherwise, the photon is a wave, so the photon cannot wave through empty space. So there has to be something. That is the ether, and the electron also, is a wave in the ether. But the electron interacts more with a mechanism built into the ether. There is a mechanism called the Higgs mechanism. It's a mechanism of the ether. I don't see why they don't see this.
Come back to this spin flip thing. Here.
Why do they need to create all these fields?
I need to tell you about a really odd fact about the universe. It's not ambidextrous. It actually cares whether a particle has left or right-handed chirality. See, left-hand electrons have this extra little something compared to right-hand electrons. It's called weak hypercharge, which, by the way, was the name of my high school garage band. It's like electron. It's the Higgs field. To understand how this works, we need to come back to this spin flip thing. Here, I need to tell you about a really odd fact about the universe. It's not ambidextrous. It actually cares whether a particle has left or right-handed chirality. See, left-hand electrons have this extra little something compared to right-hand electrons. It's called
have this extra something. Weak hypercharge. Okay. That's the chirality. That's the direction of the spin.
Weak hypercharge, which, by the way, was the name of my high school garage band. It's like regular electric charge, which lets all electrons feel the electromagnetic force, except in this case, lets only left-hand electrons feel the weak nuclear force. This cosmic asymmetry is incredibly weird, and it's part of a mystery called parity violation. It's an open question why the universe cares which direction you're spinning. In fact, it cares so much that it won't let an electron flip from left to right unless it can ditch its weak hypercharge, or flip back again unless it can pick some up. But where does this charge come from and where does it go to? You probably guessed, the Higgs field. The Higgs field is really weird. While most quantum fields hover around zero...
Okay, so in one direction it has this extra something, and that it allows it to interact with the strong force or the weak force? Which was it?
The electron is never not bumping into things. There's something in the substrate of space every...
What?
It was a type of charge, I think.
Yeah, but which one? The weak or the strong force?
Everywhere that impedes the electron. It's the Higgs field. To understand how this works, we need to come back to this spin flip thing. Here, I need to tell you about a really odd fact about the universe. It's not ambidextrous. It actually cares whether a particle has left or right-handed chirality. See, left-hand electrons have this extra little something compared to right-hand electrons. It's called weak hypercharge, which, by the way, was the name of my high school garage band. It's like regular electric charge, which lets all electrons feel the electromagnetic force, except in this case, lets only left-hand electrons feel the weak nuclear force.
Oh, the weak... I don't even know what the weak nuclear force is. I never figured that out. It's like the Z... The W and Z bosons, that is radiation. I don't know. I never understood this. I don't know what the weak force is. It's like it's always a boson. It's always a particle, or a very heavy particle boson. So it's not even like the strong force that you can. It's a force. I don't understand the weak force.
It's cosmic asymmetry.
And then he says it has an electric charge. What? Yeah, the W and Z bosons, they have a charge. Oh, I think that's the previous video we were just watching.
It's incredibly weird, and it's part of a mystery called parity violation. It's an open question why the universe cares which direction you're spinning. In fact, it cares so much that it won't let an electron flip from left to right unless it can ditch its weak hypercharge, or flip back again unless it can pick some up. But where does this charge come from and where does it go to? You probably guessed, the Higgs field. The Higgs field is really weird. While most quantum...
So there is, in my interpretation, there is no Higgs field. Rather, there is a Higgs mechanism in the ether. And the ether is the only field.
Fields hover around zero in empty space. The Higgs field has a positive strength at all points in the universe. There's a little bit of Higgsiness everywhere. In some stunning quantum weirdness, this complex multi-component field not only carries the weak hypercharge, but manages to take on all possible values of this charge simultaneously. This makes the Higgs field an infinite source and sink of weak hypercharge. Our poor electron is bombarded by a flow of particles into and out of the Higgs field from all directions, giving and taking away the weak hypercharge on infinitesimally short timescales. On its own, the electron would travel at light speed, but trapped in this Higgs field buzz, the electron feels mass. Honestly, this is a pretty wild story. An invisible and infinite ocean of some sort of charge that we feel. Quantum fields hover around zero in empty space.
Okay, what are they showing here? So, real electronness. Real electronness and location. This is electron field potential energy. Okay, so the electronness is mostly zero. But wherever it shows up, it's non-zero. But it's mostly zero across the universe. So, like, the ether doesn't wave throughout the universe. It doesn't wave electrons. There's no electrons waving except for where electrons are waving.
Space, the Higgs field has a positive strength at all points in the universe. There's a little bit of Higgs in it.
So the yellow is, let me see what it says here. Real electronness, Higgsness. So the Higgsness, so the blue is the electronness, they're not showing it. And the yellow is the Higgsness, and what is the Higgs field potential? Oh no, this is the Higgs field potential. So the Higgs field, why does it need to be so high? Wait, what was the previous one? What just happened?
Or flip back again, unless we can pick some up. But where does this charge come from and where does it go to? You probably guessed, the Higgs field. The Higgs field is really weird. While most quantum fields hover around zero in empty space,
Okay, so the electron is hovering around zero, okay.
the Higgs field has a positive strength at all points.
Yes.
The Higgs
That means that most of empty space doesn't have electrons.
Right, so I don't know what they're trying to show, but they're saying the Higgs vibrates around non-zero, whereas the electron vibrates around zero. So
Yeah.
wherever you have, I guess, a Higgs particle.
Means they're basically everywhere.
No, I mean, it's around. It's around this value. No, I don't think you get them. You usually don't see Higgs particles. They have no reason to show up. It's just, this is the Higgs field. It's a non-zero, so it's everywhere. Which is, all it means is that every particle except for photons and gluons, I think there's nothing else. Everything else interacts with the Higgs. So the ether always interacts with particles except for photons. Okay, so that's why, because the Higgs always interacts, it's a non-zero field. That's all it means. It's just, that's all.
In the universe. There's a little bit of Higgsiness everywhere. In some stunning quantum weirdness, this complex multi-component field not only carries the weak hypercharge, but manages to...
Okay, what is this? So this is the imaginary left to right, and the top to bottom is the real electronness and the Higgsness. Okay, but why do we need the imaginary? What is this imaginary? This is the location, so I think this is maybe the bounciness, the jiggling. Higgs field potential. What is the Higgs? This is the Higgs field potential? So what is the yellow? What are all these yellow?
The value Higgs field potential.
No, I think the yellow is the electron.
No, the blue is the electron.
No.
Yes.
So what are all these yellows?
Higgs.
No.
Yeah.
to take on...
No, it says here Higgs. The top one is Higgs field potential energy. The top one is the Higgs field potential energy. So I don't know what what these are.
all possible values of this charge simultaneously. This makes the Higgs field an infinite source and sink of weak hypercharge. Our poor electron is bombarded.
It's a source and sink. So it
Right.
gives
What
and takes.
is source and sink?
What?
What is source and sink? I got
It
distracted.
gives. It's always giving and taking the weak hypercharge, whatever, to electrons. So if they don't have it, it gives it. If it doesn't have it, it gives it. If it has it, it takes it.
So the weak
So-
hypercharge is like the vibration.
No, the weak hypercharge. No, I don't know. I don't know what his diagram comes to say. I don't know.
Bombarded by a flow of particles into and out of the Higgs field from all directions, giving and taking away the weak hypercharge on infinitesimally short timescales. On its own, the electron would travel
Oh, so these are from this. These yellow lines are giving and taking the chirality, the weak hypercharge.
at light speed, but trapped in this Higgs field buzz, the electron
Yeah, the blue is the electron.
feels mass. Honestly, this is a pretty wild story. An invisible and infinite ocean of some sort of charge that we've never heard of, all invented so that electrons can be left and right-handed at the same time. How do we know it's true? Well, something like this must be true, because all of the rest of quantum field theory hangs together too well. We conclude that QFT is essentially correct, but it's an incomplete theory without a mass-giving field. The Higgs field is the best, least silly option to do this. But how do we prove it? Enter the Higgs boson. Just like the other fields, the Higgs field can vibrate around its baseline value, which gives us the boson. This particle actually has nothing to do with giving anything mass. However, if we observe the particle, then it means that the field also exists. Finding the Higgs boson was the biggest mission of the Large Hadron Collider. Now that's a topic well covered in other places, so just the the TLDR. In 2012, the LHC spotted the debris produced by the decay of an unknown particle, and those decay products are consistent with the disintegration of the highly unstable Higgs boson.
Okay. What is this? What are we watching here? This is weighted events. 1.67 GeV. What do you... Oh, divided by 1.67 GeV? I don't understand. So this is basically times 1.67 GeV. Okay. So this value is about 800 times 1.67 GeV, but it's supposed to be, what did I say, 125 GeV. Energy blip from decay of Higgs. Oh yeah, this here is the 120. This is 125. This is what they predicted. But what are we looking at? So what he shows before,
LHC spotted the debris produced by the
this is the debris. Now the debris, let's say that's more straightforward. So you have a bunch of sensors that I don't know how they work, but they're probably just some sort of plates that feel energy, that feel electric and magnetic fields. I don't know. These are just sensors.
I mean, they're light sensors.
But they're like the electric sensors? What kind of
Light.
sensors? Light?
I think
Okay, but light,
by and large,
light.
they're basically light sensors on like various wavelengths.
I mean, you need to sense. But light means just photons. But there's other particles that come out of the smashing of two hadrons. Right? They're smashing two hadrons, basically two protons. How do you smash protons? They don't. I would say they smash two neutrons. Protons are
No,
impossible
they
to
smash
smash.
protons.
How can you smash a proton? They're both positive. They don't want to be at the same place. They want to run away from each other.
If you make them fast enough, it's more difficult. Yes, but can be done.
Okay. I would smash protons and neutrons, or neutrons and... Oh, you cannot smash neutrons because you cannot accelerate them. You can only accelerate an electric charge. So you can either accelerate an electron or a proton. So they're probably accelerating protons. And they're smashing protons against each other just to create a very high energy explosion. And from this explosion, because of the energy, they're creating all sorts of particles. Sometimes because of probability, sometimes these will be Higgs bosons. Because why not? Because, statistically you're going to get anything. And so how do they know it's a Higgs boson?
decay of an unknown particle, and those decay products are consistent with the disintegration of the highly unstable Higgs boson. It seems very...
So he says because of the...
produced by the decay of an unknown particle, and those decay products are
I
consistent
see.
with the...
I see how they do that. Now I'm reading here. Basically, they have like gas in the thing, and you just see where the particles go in that gas.
They have gas?
Yeah.
Oh, it's a cloud chamber. You're saying they're using a cloud chamber? I don't think they use cloud chambers. I don't think they're using a cloud chamber. They might be. It could be even gel. They could even be using some gel, but okay, and they're using some detector. Wait, what just happened?
I don't know.
Amnesiac 6, what's up? Can you hear
Hey
me?
guys.
Hi.
What's up?
Amnesiac.
Mhm.
Hey, what's up? Do you want to talk?
Oh, hello.
Hello. We're streaming a physics. We're doing physics on YouTube. Do you know physics?
I know metaphysics. Does that count?
Sure. What do you know? Tell me what you know about metaphysics.
I take I take a nominalist view on properties. And
What? Wait, you take a what view on properties? A what view? Ominous?
nominalist.
Nominalist That's
nominally.
Yeah.
metaphysics. Wait, what is
What
it?
does that mean?
What is metaphysics? Wait, he can't hear you. You
Yeah, you can't hear me, but I'm asking.
So wait, what you
Okay.
Sinus, you can join simultaneously. You can join both. You can join the Discord.
Yeah, I can be on board, but not now.
Hmm.
I'll search.
Okay, you do search. Yeah, amnesiac. What is metaphysics?
I take metaphysics to be some sort of foundational or some like um I don't know, that's a good question. I have to it's usually like abstract concepts, be like substances, time, space, like the philosophical study of that.
So what's the difference between physics and metaphysics?
Well, typically physicist is going to make some sort of empirical claim
Wait,
or some claim about
how can you
the
make
no.
how can you make a non-empirical claim?
Well, you can do analysis like what is x and what is y.
Okay, but how can you talk about something that's not empirical? Like what it, how could you, I just don't know how to do that. Like you would talk about an angel or God. You would have to
Well,
talk,
you would just talk about like you would just analyze things. Like just not all like do you know what the analytic synthetic distinction in philosophy is?
no. But why are we switching topic? I'm trying to understand metaphysics and
Well, no. There's claims that are synthetic.
I
So
don't know what
a
that
synthetic
means.
claim would be like
Hmm.
um, pigs can't fly, right? We would have to test. That's something we would have to test. Well, if pigs can't fly, then we would have to
What do you
test if
mean?
pigs can't
Wait.
fly.
Well, we don't know if
But like
pigs.
analytic statements,
Wait, why
what
can't
were you saying?
pigs? I mean, pigs fly. If you take them on a plane, they fly. Why do you say
Well,
pigs?
you know what I mean. You know what I
No,
mean.
no, I don't know what you mean. Cause like I never heard of anyone who like what
Well,
why.
a synthetic claim is something that you can test empirically.
One second.
Analytic statements
Wait,
are about
wait, wait,
things.
wait, 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 wait. Hold on. So you're claiming that pigs cannot fly. I never saw a no-fly list for pigs. I never knew that pigs are not allowed to fly. And even if you say that the FAA does not allow them to fly, that does not mean pigs cannot fly. It just means the FAA maybe has put pigs on a no-fly list. You can still
Okay,
take a
we'll just say the synthetic statements are just statements about
what?
things that we can test,
Yeah,
right?
we can test
We
whether
can test
pigs.
the validity.
We can test the validity of the claim that pigs can't fly. Why can't
Right,
pig?
right. So that's what a synthetic claim is. So an
So if I
analytic statement is just about the
even
claim of
if
the
I take
definition.
what's the definition of fly? I mean, if I pick up a pig and throw it in the air,
Or just the
is it?
meaning of things.
Wait,
I don't
what?
think I don't think you can still have a meaning. You can have a meaning and not a definition. Like there's existence of brute facts and
Wait, I'm lost. You're losing me. You keep losing me. What, what is meta? I don't. Okay, I'm dead. Okay, can you say something that I can understand? What? Do you understand what metaphysics is or what synthetics is? Like you're making claims that he's gone. We
He's
lost him.
gone.
Yeah.
Okay, I mean, I can explain. Metaphysics is basically it's in essence the study of concepts.
I don't know what that means. I don't know what
What
the
that
study
means,
of concepts is.
I mean, it's the study of abstraction, really. That would be a
What?
better one.
I don't know what that means.
Yeah.
I
Okay, I
don't
read the
know.
definition. The branch of
No,
thought.
don't worry about it. No, don't worry about it. I don't see
Okay,
the
fine.
purpose. Like I'm a pure scientist. I
No,
don't
like
care.
something like, for example, your stance on morality and stuff like that is basically that's part of metaphysics.
I have a scientific stance on morality.
You have a
Meaning,
scientific stance on morality. Okay,
yeah.
fine, you can say that.
Yeah.
But like something like the scientific method is technically part of metaphysics, is epistemology. I think
The
epistemology is
scientific the
metaphysics.
scientific method for
Right.
me is the axiom is an axiom. It's the ground truth of my science my being a scientist.
Okay, now supposedly metaphysics is not the same as epistemology is not part of metaphysics.
Wait, what is epistemology? Just
Epistemology is the study of knowledge.
okay.
So that makes metaphysics
So
just
let me just I'll just say my theory of knowledge is science. I don't know of any other way of knowing but through science.
so okay, so that's an epistemological position.
Okay, that's good.
Fine.
At least I understand the word epistemology. Let's continue because it's killing me. Let's see. So this what's his name? Do you remember his name?
What's name?
He's like he's a
What are you talking
professor.
about?
The screen.
Oh, the guy on the screen.
Yeah, I
I
forgot his
don't
name.
know. I call him PBS space time.
Oh, okay. Anyway, so he says. So I remember this when they showed this the day they found the Higgs boson. So this is the Higgs boson. Okay, so they said at 120 around 125 GeVs. I don't know what M gamma gamma is, but this is giga electron volt. A giga is a billion or a
Yeah.
billionth.
So that's
No, it's a
energy.
billion. What?
So that's energy.
Yeah, which is
Energy.
mass. Mass
Yeah.
and energy because m equals v E equals mc squared. All right. So this is the energy of the particle. So it's like it's 125 billion electrons. That's how much it weighs. It's pretty heavy. But what are all these? So these are all the particles that they found between 0 and I don't know what. So all the particles.
No, this looks like something decaying.
What do you mean? What's decaying?
Like the energy going to zero. Weight and events. Okay, so that's weight and events. So this is just a measure of events. Yeah, there's nothing special.
These are just the like it's the
Just how
weights.
many events there were at that level of energy.
Oh, just this is like a weighted average.
It's not. Yeah, it's
Meaning you
weighted
had
average.
so you had events at 0 mass, events at this mass. So this is the distribution of the events
Yeah.
and their mass. And they said at 125 because of this specific experiment they were conducting. So this specific experiment, I don't know what I mean. They don't have a specific experiment. They just clash hadrons, protons into each other. They're just clashing them and getting. This is the distribution. So at 0, you actually had a very. There were a lot of events. Of course, this is exactly as you'd expect to have a lot of low energy and very few high energy. But why do you have this suddenly this thing going up? Meaning at 125. So the way they run the experiment, I think they run it at low energy, greater, and at this energy, when they get to. But I don't understand. I mean, if you're not controlling this is the answer, and this is the input. So you're modifying, right? They have a dial at the wherever they sit. There's a place where they sit and control the experiment. So they turn up the energy of the experiment. This is the energy of the experiment. This is the energy of the beams that are colliding into each other. It's a Large Hadron Collider. So they can control the speed of the beams, which are always, I think, at very close to the speed of light. So the beams, there's two beams flying across each other, into each other. So how could this be zero? It's zero? It's zero energy? This doesn't make any sense. So I don't know, because the way I would run the experiment, okay, this is zero energy. Probably at zero there's nothing. So this is like one giga electron volt, meaning what I don't understand. I mean, honestly I don't know what they're plotting here, so forget it. Do you understand this plot?
Yeah, I do.
So how do you control, like, this is the control variable, right? You control this variable, right? This is the input, and this is the answer of the experiment, right? And you're getting at 125, right? You're getting a zero. You're getting an inflection point. You're getting a local maxima, right? And this entire thing, there's no local maxima. There's no rest points. There's no zero derivatives. Zero value. This is the only zero value derivative on this graph.
Yes.
Okay.
So
So how do you?
They just basically find a bump of energy at that level.
What do you mean a bump? What's the input?
A bump of
What do
waves,
you?
a bump of events
I
at
don't
that
know what
level.
that means. What are you controlling?
Yeah,
How do you
this has
control?
energy, but okay.
Tell me how you ran this experiment. Can you tell me the protocol of the experiment?
Okay, that's a little bit more detailed. But what I'm thinking they do is that they have particle collisions, and then they measure the energy of each event in the particle collision. That's basically it.
Wow, I can't believe
And they
I'm
just
so
get more events at that. They just get an unexpected high number of events at that level. Although I don't know if this is like the interpretation needs to be
Anyway, forget it. Let's continue. I don't know. I mean,
because it could just
it
it could be
doesn't matter.
something else really.
I don't understand this. I'm
Well, I
falling
mean
asleep.
if the prediction is that that will happen, that's quite a specific prediction.
I
So
cannot understand what you're saying.
now if the prediction is that, that's actually a rather specific prediction. So that's good.
But what is the protocol? Tell me the protocol of the experiment.
I mean,
What's the
I can't
protocol?
really tell you for sure the protocol. I can tell
Don't
you
tell me
that.
for sure. Tell me your theory. What is the protocol?
Okay, what I think is the protocol is that they have a particle collision. They measure the number of events that they catch over
Wait a minute.
many
Hold on.
particle
Wait,
collisions.
wait,
Up
wait,
to
wait,
many
wait,
particle-
wait, wait, wait. At what energy levels were they running the experiment?
What energy levels were they on?
Yeah, what was the speed? What are they? How are they controlling this? How are they getting this plot? Did they run it at this energy and get this point? Run it
I
at
mean,
this
this is
energy,
probably
get this point?
from the particle showers that they get when they collide something.
So they collided at like, I remember what they did. Every couple of months they restarted the collider. They said today we're going to be running at the beginning it was like 50 giga electron volts. And then they shut it down and they fixed it up and they said, okay, today we're going to start running experiments at 100 giga electron volts. And then they shut it down for a couple of months for upgrades. And then today they're going to reopen it and we're going to run it at 125 or 126 giga electron volts. And we expect to see the Higgs boson today. I remember this. And
okay,
then
so that's it.
okay. So when they ran the accelerator at 125 at around 125 giga electron volts, they have to run it all the way to here to get I think they were running at about 125. 1 second, I have messages. Oh, Andrew. At basketball court, I've been there since 8 and it's 12. Okay. I'm tired. I'm so tired. Okay, so let's say they ran the experiment at about 125. And this is the distribution of events. So at 125 giga-electron volts, some of the events were low energy, low GeV, and some of the events were greater GeV. But at 125 giga-electron volts, they had a bump of this particular GeV, and that's the Higgs boson. That's what they said. This is the Higgs boson. Now there's millions of these events. Well, it's approximately it's 1600, but it's a weighted events per 1.6 GeV. I don't know why it's per 1.67 GeV. I don't understand. But it's just a weighted event, meaning they had this many events, or this many percent of the events. Maybe it's like a percentile. It's difficult to say. Maybe it's out of 2,000. Out of I don't know.
Okay,
but
so weight and events, probably some kind of weight and average of events.
Yeah, it's like a percentile. It's a certain expression of a percentile. Like a lot of the events were low mass and a little less frequent. This is basically a frequency. This is the frequency. How many events did we get? I'm assuming.
Yeah, the per 1.67 GeV, that's kind of weird.
I don't know.
Give that
Anyway,
to ChatGPT,
no, forget it. Nah,
yeah,
I'm
I
not
can
gonna
use
go.
that
No,
ChatGPT and
it's
it will
good
just
enough.
follow.
No, it's good enough. It's good enough.
Okay,
I'm gonna die. My brain is honestly falling asleep. So, okay, so they said, okay, when we ran at 125 GeV, the experiment. One second. There's no one watching, by the way. We're all alone. So at 125 GeV, so this is the distribution, and they anticipated this. Now, how can you predict this? I mean, this is the most ridiculous prediction. This is why it's a very Bacon. This is science according to Bacon. This is gold standard science. This is very high quality science. So to claim, like you claiming that you can get anything and then this prediction is meaningless. No. This prediction is gold standard. This is the gold standard of science.
Disintegration of the highly unstable Higgs boson. It seems very likely that the LHC did produce the Higgs boson, which in turn would mean that the field exists. The whole story is now coming together very nicely. But there's still a lot we don't know. The Higgs boson is hopelessly unstable, and it decays in around 10 to the power of minus 22 seconds, which makes it very difficult to study its actual properties. Could the Higgs field also explain things like dark energy, inflation? There are reasons to think it might. We'll come back to those in the future. For now, we'll be delving deeper into the mysteries of matter and time in the next episode of Spacetime. In the last episode, we told you how to build a real astrophysical black hole.
Okay.
I like the inflation.
So we don't know how the Higgs mechanism works. Except for, I mean, this is where I can't believe that I picked up so much from so little. And that's all I heard many years ago. And from that, I told you the story of how it works. It's interacting with the particle. The particle wants to fly at the speed of light, and it's just interacting with it. It's just changing its direction. And changing, well, with an electron, it's changing its spin. So it's I think it's basically as I said.
Okay, let him continue, because he hasn't explained how the mechanism
He's done.
works. He told us about how it was
finished.
found or something. He hasn't
He
explained the
finished.
mechanism.
We watched him until the end.
He finished.
We watched
Yeah,
him
I
until
changed
the
tabs.
end.
I thought there was more, but he doesn't explain the mechanism. Like, where's the mechanism?
What can I do?
Like, isn't explain
Yeah,
the
it's
mechanism.
good
He talked
enough.
about
No,
fields. But let's go.
no.
He talked about fields. And then now there were his fields, and then now there was his experiment and
He
mass.
says initially
Wait,
every
and mass.
particle.
Like, what
he
does he
said-
explain here?
He said initially every particle has no mass,
Yeah.
and they all travel at the speed of light, and they all have a single chirality, a single spin.
Okay, you talked a lot about chirality for whatever reason.
Yeah, no, because that is, it's the interaction. It switches chirality, so it switches direction and it switches the chirality. 1 second.
Okay, yeah, I did. That's a lot. And he said we measured it. He said like a bunch of things that are completely out of the scope
Wait, somebody was
of the
texting.
title.
No,
Okay,
it's
so
okay. Why you don't like? No, it's fine. It's the Higgs mechanism explained. It's perfect. So and then
what's the mechanism?
the
We know
mechanism.
that the tiny neutrino
Yeah,
presence,
I've
and it was the
heard
measurement that
the
those neutrino oscillations.
He's talking
Anyway.
about neutrinos now, or for whatever reason.
Whatever. Like the neutrino oscillates, but that's irrelevant. Anyway,
Okay,
this is the speed.
What's
It's
the
the speed.
mechanism?
So the photon spins only in a single direction because it doesn't interact with the Higgs, and therefore it's only moving in one direction. But here is the electron. The electron moves slower because it's interacting. Maybe this
Okay,
is not the
cool.
same video.
Still not explaining the mechanism at all.
Look, maybe I heard it on a different. I just remember him explaining it, but I remember.
Yeah, but continue. Maybe we missed something.
No, we went through every word.
Incredibly weird. And it's part of a mystery called parity violation. It's an open question why the universe cares which direction you're spinning. In fact, it cares so
he's
much
talking
it won't
about
let an electron flip from left to
chirality.
right unless it can ditch its weak hypercharge, or flip back again unless it can pick some up. But where does this charge come from and where does it go to? You probably guessed. The Higgs field. The Higgs field is really weird. While most quantum fields hover around zero in empty space, the
Okay.
Yeah, he explained
So
this
most
part,
fields
which is like, okay, that's fine
hover
mathematically,
around-
I guess.
So
Still
he
doesn't
said
explain
what?
it.
does it go to? You probably guessed. The Higgs field. The Higgs field is really weird. While most quantum fields hover around zero in empty space, the Higgs field has a positive strength at all points in the universe. There's a little bit of Higgs
Is the yellow the Higgs field? I don't understand.
Yeah.
What is this? What is this? What is this wave? It's like, I think he says it's non-zero. What do you mean? I don't
No, that's
understand. It's-
electrons.
What?
That's the electron field.
What?
That's the electron field. The blue is the electron field.
And the yellow is the Higgs? So why
Exactly.
does it say here Higgs field? And what is this? This is the
Right,
sombrero.
potential
They
energy,
say
correct.
that the Higgs field energy level is a sombrero. So this is the lowest energy.
Sombrero.
Yeah, it's a sombrero.
Yeah.
So this
Yeah, I
is the
guess
lowest
that's the
energy.
highest probability, no? Wait,
I don't
yeah, it
know.
doesn't explain what
Higgs
the hell
everywhere.
it
In some stunning quantum weirdness, this complex multi-component field not only carries the weak hypercharge, but manages to
I
take on
see.
all possible values of this charge simultaneously. This makes the Higgs field an infinite source and sink of weak hypercharge. Our poor electron is bombarded by a flow of particles into and out of the Higgs field from all directions, giving and taking away the weak hypercharge on infinitesimally short timescales. On its own, the electron would travel at light speed, but trapped in this Higgs field buzz, the electron feels mass. Honestly, this is a pretty wild story. An invisible and infinite
Okay, I don't understand, but I don't think this is the best explanation. Maybe this one was a better one.
Fermi-lab physicists really care about the mass of the W boson. They spent nearly a decade recording collisions at the Tevatron Collider and another decade analyzing the data. This culminated in the April 7th announcement that this obscure particle's mass seems to be 0.1% heavier than expected. So why do we care? Well, because understanding why this particle even has mass was one of the most important breakthroughs in our understanding of the subatomic world, and because measuring its precise mass either doubles down on our current understanding or reveals a path to even deeper knowledge. The Fermi-lab discrepancy is a tantalizing hint of the latter. The timing of Fermi-Lab's discovery is weirdly convenient. Over several previous episodes, we've been building towards an understanding of how the forces of nature are unified. The most powerful clue driving this is the weirdness of the weak force, in particular, the particles that carry this force. Its W and Z bosons have a property that we once thought no force-carrying particle should have. They have mass. The W bosons are especially weird and they also have electric charge. This allows the weak force to trespass on the province of electromagnetism, suggesting a connection between the two. This connection hints at a unification of the forces of nature. The path to that unification leads to the Higgs mechanism, which not only explains the mass of the weak bosons, but teaches us about the nature of mass itself. To get to all that good stuff, we need a bit of a refresher on the episodes that led to this. Field and forces and symmetries and all that. Similar to how the fabric of a drum has vibrational modes, so does the fabric of reality. Every point in space can wiggle, twist, and oscillate in different ways. A quantum field just represents one of these modes. These wiggles are quantized. They come in discrete packets of energy that can move around, and those are the particles of the field. One special type of field is the gauge field. These arise from the fact that physics often doesn't care what coordinate system you use. The laws of physics are symmetric under certain transformations. For example, physics works the same no matter where you decide to center your XYZ axes, or where you put the 0 point of your angles in polar coordinates. We saw in our episode on Noether's theorem that these symmetries lead to conservation laws. In quantum mechanics, this sort of redundant degree of freedom leads to a gauge field. We've seen an example of this. The exact phase of the quantum wave function from one point of space to the next, local phase, doesn't affect measurable quantities, only relative phase masses. When we enforce this requirement, we find that we have to add a new quantum field to the Schrödinger equation that lets the universe
Wait, what just happened? Somebody came in. Alright, never mind.
Counteract these phase shifts. That gauge field turns out to be electromagnetism, and oscillations in this field are the photon, our first gauge boson and carrier of the electromagnetic force. So, one of the fundamental forces arises from a symmetry of nature, in this case the fact that the laws of physics are invariant under changes of local phase. The set of transformations that can change local phase are an example of a symmetry group. In this case, unitary group 1, or U1. These transformations can be represented with just one
I don't know anything about this symmetry. It's like something that I'm trying to figure out.
number, in this case rotation of a phase angle vector of unit length. See this episode for all of the nitty gritty. This is just a refresher. In the next episode, we tried the same trick to explain the weak interaction as arising from symmetries. We saw that we could invent a pair of totally abstract degrees of freedom and demand that the universe be invariant to transformations of these. We call this symmetry group SU2 for reasons. That requirement gave us a new...
Yeah, we need to study symmetries. This is
No, I think it's just going off topic like crazy.
No.
gauge field that had 3 force carriers.
No, look, this is mainstream science. I mean, I don't have a problem with mainstream physics.
That look awfully like the weak force bosons. So far, so good. Except that the predicted particles are massless, while the real weak force bosons are, as I mentioned, pretty hefty. And that is a huge deal breaker, actually. Massive bosons break gauge symmetries. According to something called Goldstone's theorem, all gauge bosons are massless. So far, so bad. But we're going to forge on anyway and hope that this all gets sorted out. Another problem with this first pass at the weak force is that it has absolutely no connection to electromagnetism. These bosons do have properties that look like weak isospin and weak hypercharge, but no electric charge. In our universe, these three quantities are sort of locked together, only
No, I have no idea what's going on.
taking on certain values relative to each other. To see if we can duplicate that in our theory, we need to combine the U1 and the SU2 symmetries so they all apply at the same time. We call this combined symmetry group U1 cross SU2. The resulting gauge...
Are you falling asleep, or am I the only one falling asleep?
No, it's okay.
Yeah,
I'm
I just want to speed through this to see if this is where he explains gravity the way I explained it. I mean, mass.
field still has bosons that look a bit like the photon and the 3 weak force bosons, but the latter are still massless, and the resulting charges are completely unconnected to each other. They're all free to be whatever they want, unlike a real universe where isospin and hypercharge are tightly coupled, and their combination defines electric charge. So is it time to give up on this symmetry stuff? Well, there's one more long-shot clue. I said that massive bosons break the gauge symmetry, but what if that's okay? We've also talked about the idea of symmetry breaking before, using this example of a bunch of bar magnets. These magnets have high temperature, which makes them move randomly, but as the system cools down, this random thermal motion gets overpowered by the magnetic interaction, and they all end up aligning. The equations of magnetism don't start out with a preferred orientation, but in certain conditions, namely cold ones, the system chooses a preferred direction. This is an example of spontaneous symmetry breaking. So if a bunch of magnets can live in a state that violates the symmetries of their ruling equations, maybe the universe can too. Here's another analogy. Consider a ball rolling back and forth in a valley. The equations describing its motion are symmetric between left and right because the valley is symmetric. Now imagine it wasn't one valley, but 2 valleys with a hill in the middle. The system is still symmetric, but if the ball starts at the top of the hill, it will...
That's not the Higgs. I don't think the Higgs is like that.
randomly roll down into one of the valleys. Now the current state of the system has a broken...
Wait, I have a message. In general. Oh, Judas can defend his position when his weird position. Oh my god. Okay.
symmetry, even if the symmetry of the landscape
Andrew
remains.
wants to talk to me.
Who wants
No,
to
no,
talk to
continue. I just saw it now.
you? Somebody wants to talk to you?
Yeah, Andrew.
Andrew wants to talk to you now, but we're listening to the stream.
Yeah, not now, but...
Yeah. Oh, okay.
Let's see if we can break the symmetries of the universe in a similar way. The equivalent of the simple valley does exist. A quantum field can oscillate around some 0-point value like a ball rolling back and forth in the valley. The walls of the valley are just the potential energy, the energy stored when the field moves away from the 0 point, trying to pull it back to the center. Graphing this, the vertical represents potential energy and the horizontal represents the field strength. Particles of the field are just oscillations of its field strength across the lowest point, where the field strength is 0. But if there are no particles around and the field just sits at the lowest point, we call that the vacuum state. Easy stuff, right? In that case, you won't mind seeing the math. Okay, don't freak out. It's not on the test. This is a Lagrangian, something we've covered before. It's really just the difference between the kinetic energy and the potential energy in the field. Our plot was of the potential energy part. This particular Lagrangian describes a simple quantum field made of massive particles which interact with each other. Let me talk you through the hieroglyphics. Firstly, phi is the quantum field itself. It just means there's a numerical strength of the field everywhere in space. The potential energy part is the shape of the field, and it's made of various powers of the field strength, representing ways that the field particles can interact. For example, this phi to the power of 4 term says that the particles of the field interact with particles of the same field with strength lambda. This phi squared term represents the field interacting with itself. That self-interaction is what leads to the property of mass. Gauge fields shouldn't interact with themselves, so shouldn't have a phi squared term. And that means this probably isn't a gauge field. The gauge field is a thing that comes from the degrees of freedom within this field. This particular Lagrangian has the simple symmetry that it's the same if you reflect it around the y-axis. If we complicate things by adding a second field component, phi1 and phi2, we get a parabolic bowl. If the current state of the field is at the bottom of the dip, then it has a single continuous degree of freedom, and that you can rotate this thing and nothing changes. That would be
I can't believe anyone in the world understands this video.
Yeah, I'm getting it. Pretty much.
You're understanding this video?
Yeah, I mean it's a bit fast, but I would watch it slower because
You want to tell me
it's a bit heavy.
1.5 million people watched this video and got it?
No, probably didn't get it. Most of them.
A global U1 symmetry.
Yeah, I
We're
mean I
printing
can
out
see, but
electromagnetism.
is it's a bit different because it's explaining the gauge field. So
means
they
requiring
doesn't really give mass per se. It's the gauge field.
Local U1 invariance. We need the laws of physics to still make sense if there are rotations from one point in space to the next. That means adding a new gauge field to the Lagrangian that allows the angle of this rotational degree of freedom to vary. Oscillations in that field would be a gauge boson. You can think about those oscillations as the angle twirling around freely, and it doesn't need any minimum energy to oscillate, so the gauge boson is massless. On the other hand, the particle of the original field needs a rest mass energy to be able to oscillate up and down the potential walls. So while this potential has its own massive particles, it doesn't give us massive gauge bosons. Let's make a slight change. We're going to switch the sign in front of the mass term. Then the potential will change to this, just like the two values we saw earlier, but now the second field component gives us this 3D shape. It's called a Mexican hat potential. This potential shape is the heart of the Higgs field. It's still a symmetric potential. It has the same global U1 symmetry as the original, but if the universe suddenly transitions from the old potential to this one, then we have a problem. The field's strength would find itself at the top of the little hill, but then quickly roll down in a random direction. The new state of the field would not be symmetric to the same rotations because different points around this valley correspond to different physical states. We say that the symmetry is spontaneously broken. The current state of the field is a state of broken symmetry, even if the global field shape keeps its old symmetry.
This is not about the Higgs mechanism.
This is just like how the field of magnets can be in a state of broken symmetry.
How is explaining the mechanism actually?
Even though the overall equations of magnetism have not changed. The transition from the central bump to the valley is an example of vacuum decay, and we saw how this can lead to the creation of cosmic strings in a recent episode. The cosmic strings are perhaps the least interesting part of this process. Once the field has reached the base of this new minimum, we have a new stable vacuum state. But this state is very different from the original for two reasons. The first is that the lowest energy state, the vacuum state, isn't where the field strength itself is zero. So this is called a non-zero vacuum expectation value. The original massive particles of the field now oscillate in the radial direction, but no longer centered on the zero field value. And this is the Higgs boson. The second weird thing, there's not just a single vacuum state, there's a ring of valence states. The universe will just have chosen one state randomly. But the field can also oscillate along the base of the valley in what we'll call the theta direction. The resulting particle is called a Goldstone boson, and it's massless because the valley is flat. There's no energy differential. However, this is not a gauge boson because location around the valley...
Alright, I'm dead. He managed to kill me. Let's
There's lots of bosons.
It's lots of what?
Bosons.
Yeah. Yeah. Okay. Let's get back to the
No,
hard
in
work.
the end, this looks a lot like just different field modalities.
I have no idea. I don't understand. I
This
don't.
just looks like a lot of different field modalities.
I don't know what that means.
Like different types of perturbation in the field.
I don't know what that means.
I don't know.
I
I don't know how to explain.
It doesn't matter. It's okay. It's fine.
Gnostic Judas hates me now.
Who?
Gnostic Judas hates me. Your friend Judas hates me.
Why? Oh.
Because I played around with him.
No, don't do that. Don't be mean.
I like being mean sometimes.
No. Stay away from that. Stay away from that. It's always bad. It never
Well,
ends up. What's the purpose? It can always backfire. You can always just gain one more enemy. Well, why would you want to gain an enemy? What's the benefit? What's the benefit? It's much more difficult to gain a friend, and then it's much more rewarding.
It could, but like in this case,
No, like when you meet someone in the beginning,
it's
you
like
wanna,
I mean I don't have anything against him. It's just like very emotional.
no, you're hurting his feelings, so he's becoming emotional.
Come on,
When a person
you
gets
have to
upset,
be a little bit, tough.
no. When a person gets upset, the first thing you need to do is let go and tell him, "I did not mean to get you upset." That's the most important thing to do.
Okay, fine.
Look, the question is, do you want another enemy or do you want another friend? It's easy to gain enemies, it's difficult to gain friends, but it's much more worthwhile to gain a friend. When you need him, he'll help you.
Alright, your position is very reasonable, so I can't contest it.
Yeah. I'm just being egoistic. Because I'm an
Yeah, being
egoist.
logical.
Well, I don't know. Logical. I don't know if I'm being
Yeah.
egoistic. I want to maximize my well-being. So I want to maximize the amount of friends. I want to minimize the amount of enemies.
Okay, that
Okay.
makes sense.
Yeah. Okay. Let's read the paper. So proof of Einstein's special. Oh, I wanted to show you Lenny.
Oh yes, that's true. Well, I forgot.
Yeah. So here is Lenny. So Lenny Susskind astonishes lecture on debunking quantum gravity. So all he says, I have no idea what he was talking about because I disagree with EPR, Einstein, no, EPR, Einstein Rosen bridge, ERB. Oh, I guess there's no term for that. So he's assuming an Einstein Rosen bridge, like a black hole connecting two parallel universes. I don't believe in that, and I don't need it in order to talk about getting information out of a black hole. So we actually had a discussion about this. I wrote the other day before.
Hydrodynamics of entanglement. That's a strange
No.
sentence.
Um, okay, we just need to look for black holes in this discussion. Black.
Yes.
Oh, you cannot search?
No, I'm reading the initial part of the video.
No. First I wanted to discuss what I wrote, but there's no way I can do a search on this page. Control F doesn't work.
Control F should work definitely.
It's not working because oh wait, I'm sharing the wrong tab. So how do you search this thing? I want to search this for the word black holes. The horizontal speed.
Okay,
did
you
I
have a
write-
search bar on the top right.
This one? When I do
Yeah.
Control F, okay, mention has, maybe has black.
I don't know what's going to appear.
A quite massive particle should grow into very. No, let's look for entanglement. Entangle. You should look more into. Okay, here it is. We should be able to use. There it is. So.
You can click.
So we should be able to use entanglement to scan the internals of a black hole. I don't see the contradiction. So you entangle two electrons, meaning you create them out of the same energy, so they both have opposite spins. You throw one of them into a black hole, and then you measure the electron that you have in your hands. And the results of the measurement should tell you something about the electron that fell into the black hole. Entanglement is instantaneous communication across the universe. The black hole.
Okay, so I remember what I answered to that.
Yeah, let me just finish because we're recording. I just want to make sure everybody knows. So the black hole event horizon should have absolutely no impact on the information that we get through the measurement. The black hole, so yeah.
Okay, you can go if you want.
Go where?
Oh, we can keep going.
Okay, so let's talk about using. This is called black hole scanning. How do you scan?
If you're going there, let me just tell you that entanglement is very, very easy to break.
What do you mean break?
Yeah, if you have an idea that an entangled particle should You know, like you can do whatever you want to it and it will maintain the entanglement state. That's not true. Entanglement is very fragile.
Yeah, I'm not saying it's not fragile. It's not
It's like
fragile.
very, very fragile.
Fine. So then you have to conduct this experiment very carefully.
It's kind of impossible.
Why? Why is
Well,
it
it's just
impossible?
about and like the party. This is why I don't really believe in entanglement. It's because if you do like something asymmetrical,
Wait. What do you mean you don't believe? I mean, entanglement must be true for this universe to work.
not
How else does
necessarily.
this Wait. Then I don't understand this universe. If entanglement doesn't work, then I cannot understand this universe. So
Oh,
here,
this is what it is.
so okay,
No,
so
but
here.
like the problem
Wait,
with
wait,
entanglement is that if you make an asymmetrical measurement, it doesn't
wait,
work.
wait. Hold on. So I take an electron and I move it to here.
Okay.
Thereby, right, this is the minimal. Okay, we're assuming Planck's constant. We're assuming E equals HF. So we're assuming that for every frequency there is a minimal energy that you can create. So let's take the lowest frequency with like a very, very big radio wave, meaning you take this electron and you slowly, very, very slowly move it to here. So you've just sent a very long wave, shock wave, very long wavelength, shock wave through the universe, right?
Mm-hmm.
Right, this is an electromagnetic wave. This is a disturbance. If you have a test particle, so before, let's say it's an electron, so before it felt a force this way, and later it felt a force this way. And all the test particles in the universe are feeling this change. But the progression of this wave is at the speed of light, right?
Mm-hmm.
This is an electromagnetic wave, just like Maxwell. This is Maxwell's equation. This is absolutely Maxwell. There's nothing here that is not Maxwell. So this is based on this is experimental. The only thing that is not from Maxwell is Planck. Is that for every frequency there is a minimal energy that you can endow on an electron. You cannot endow less than.
Yeah,
So
but
whatever you
that's
did
also
to
experimental.
wait, what?
Yeah, but Planck is also experimental, so it's okay.
I'm assuming Planck's equation. We still need to go back to the
Ultraviolet catastrophe.
ultraviolet catastrophe. We need to figure that out. Yeah, most videos are no good. All videos that I watched are no good. Anyway, so so there is a minimal energy. Let's say that is the minimum energy that you endowed on this electron. That is E, some E. Let's call it E naught. It's some minimal energy. Now this is also known as a photon. I mean, that's just a name. It doesn't matter. Anyway, so now let's say there is this wave expanded through the visible universe. And then one day it interacted with an electron here and an electron here simultaneously. Now, because of Planck's principle, you cannot endow the energy to both electrons. Right? Only one of them can move or can experience. Only one of them can be moved, what we call a photon. Only one of them can absorb the photon. Can't be both, right?
Yeah, you already explained that.
Right. So why are you denying it? Let's just finish the explanation. So right? So let's say it picks this one. If it picks this one, instantaneously it has to not pick this one nor any other one.
Why does it need to pick anyone?
It doesn't. But it's probably gonna pick. It's at the end of the day it's gonna interact with something. What do you mean?
Why does it need to be an electron?
So how do waves travel?
How do waves travel?
I mean, a wave interacts. At the end of the day, waves interact. Like my eyes, I see light. How do I see light? The only way I see light is a photon hits an electron in my eye and causes it to shake and creates, I think, a chemical reaction. I think the way the eye works is it's unbelievably complex. You cannot believe the cascade of chemical reactions every time you notice a photon. Every time what? What?
I have a notion.
No. If you never studied the actual, the cones, you actually have to study the cone chemistry. It's unbelievable. You cannot imagine how many steps take place between a photon hitting like the detector in the eye and the eye nerve and the retina nerve cell transmitting an electric output or converting it into an electric output. There's like a cascade of chemical events. This then causes this and causes this and causes this. And that is just the beginning of the electric current in the cell, in the neuron. And then it has to communicate to another neuron, another neuron, and then it goes to the LGR, the lateral I forgot my terminology. The LGN, the lateral geniculate? Oh my god, the lateral geniculate.
It's the LGN, it's fine.
LGN?
That's what you said, right?
It's a nucleus. It's a nucleus in the thalamus. It's like when I cannot discuss brain. I mean, I can discuss simple brain notions, but not actual brain theory. Anyway, and then it gets to the LGN, and then from the LGN, it has to communicate with V1 in the actual in the back of the head. I mean, the LGN sits basically on top of the nerve cord. What do you call the nerve cord? That's like on your back. Your back contains. Oh my god, I forgot all my brain science. Jesus Christ. Anyway, let's get back to this. So, right? So it can only if you want to respect Planck's equation, then only one electron can experience E naught, the photon. Only one electron should move, right?
I think this is a bit different. Like, for example, Planck's energy says there's a minimum energy to produce perturbation in the medium here.
Wait, I don't understand what you're saying. What?
If we combine Planck's result with your theory, or with an ether theory, then H would be the minimum energy to produce a perturbation in the medium. Right?
Wait, this is not my theory. This has nothing to do with my theory. This is just...
Okay, it's an ether theory.
No, this is not ether. This is simple...
Okay, it's not even ether, but okay, whatever.
There's no ether here.
But that's the minimum. That's the minimum amount of energy that is required to produce a photon of that.
I would say
frequency.
I would say that this is quantum Maxwell's this is quantum This is QED. I would say that this is QED. This.
Okay, but like once you produce a wave, you can impart just as much energy as you want on the electrons or not.
You can't.
You
You
can.
cannot. You cannot impart any energy you want on this system. You're limited. You're
No,
limited
it's
by
like
this.
you're limited in the amount of energy that is needed to start the wave.
No.
No?
You're limited in the amount of energy that you can impart on a system.
Okay, let me ask ChatGPT for that.
What? What do you mean? This is Planck's equation.
Wait.
This means that for a given frequency, you multiply by h to get the minimal energy or the energy.
Okay, I'm asking
Right? For a
ChatGPT
given
about this.
frequency, this is the energy of the wave. The energy of a wave but notice that there is no amplitude. How can the energy depend only on the frequency?
No, the energy is the amplitude technically.
No, I don't know. I don't know. But I don't know. Let's ignore Planck's equation. Planck discovered that, right, through the Planck didn't discover it. Einstein, you can even argue that Einstein through the photoelectric effect. So he said, you're shining a light, you're shining waves on a metal, and then you get a negative current. Right?
Yeah, wait.
So
I'm
this is
asking
the plate.
ChatGPT. I'm asking ChatGPT for this scenario,
Why?
just to see what the conventional
But what do you mean?
explanation is.
This is Maxwell. This is Maxwell with the minimum energy concept of the photoelectric effect. I'm just using the photoelectric effect in Maxwell's equations.
Yes, I know you are.
Let me ask, what is going on?
Okay, so it says it would happen exactly as you say.
What does it say?
Says it would happen. Says basically the exact same as you.
Tell me.
That okay, I will read it. Wait.
You can share your
If the
screen.
wave, no, I'll just read it. If the wave corresponds to a single photon with energy E equals to hf, quantum mechanics dictates that this photon can only be absorbed by one electron. If the wave front reaches both electrons simultaneously, only one of them will actually absorb the photon. The exact electron that absorbs the photon is determined probabilistically. The photon cannot be split, it will transfer its energy to one electron.
And that's entanglement.
Yeah, I don't think they consider this entanglement, but
It's instantaneous. This is instant communication. This is spooky action at a distance. This is instant
I'll ask
communication.
if there's been an experiment like this.
What do you mean experiment like this? What do you what you're saying? You're saying you're violating conservation of energy. What do you mean? Has there any time been an experiment that violates conservation of energy? That's what you're saying. You're saying that it's
No,
possible.
not really.
What do you mean? This is you invested a certain energy. This is the investment, and you're gonna get exactly one of them is gonna experience this motion. This energy will be experienced by this electron. Only one of them, and that's going to be the same exact energy. If it's going to be two of them, then or many of them, then you're going to. This is an explosion. That means this universe is unstable. There's no conservation of energy. You keep creating energy out of thin air, and that's an explosion. This universe explodes, according to you. What do you mean? Has there ever been an experiment like this? This is called this universe. And this has to be instantaneous. This is instant communication across the visible universe. How can a single system be selected probabilistically? How? That's because it's instantaneous. One of them is picked and the other one is not. How? How does the wave know? That's instant communication across the visible universe. Even beyond the visible. It's not even limited to the visible universe. Even outside of a black hole, this information can travel outside of a black hole, and that's how we can use it to scan a black hole. Right? And this has nothing to do with ether. This is just irrelevant of my research into ether. This
Okay,
is just.
but how would we do this then to scan a black hole?
Wait, I don't understand what you're
What
saying.
would we do with this scan a black hole?
What do we do to scan a black hole? One
With
second.
this.
Let me just. 1 second. I just want to listen to a message.